Yes. Okay. And this to remove the light? Yes, I don't want to light now. Just the first 10 minutes. Thank you. So this is not working. It will come. Okay. Yes, this is okay. Thank you very much first because you're here. And we talked yesterday and the days before about different ways of measuring the distortion of mappings from one surface to another surface. The first way was this Lipschitz distortion, which was introduced by Thurston as a metric on Teichmüller space. I will talk about this later. Yesterday we talked about the quasi-conformal distortion, which is a measure of how a map differs from being conformal or angle preserving. I want to mention this third way of measuring distortion of maps. It's taken from a paper by John Milner, 1969, and so it is rather old, but at the end I will show you some remarks which Milner formulates on this paper in volume 1 of his collected works, which appeared maybe not long ago. So the problems that he raises are still ongoing, and he formulates a new open problems, which I will tell you about. And one of the features of this kind of problems is that it's only topology, in fact, topology and a little bit of metric spaces. You don't need to know a lot of things. You not need to learn fancy theories to work on problems like this. So let me tell you how this how this distortion is defined. So we have a map. Wait a minute. Okay. We have a map here, F, from a subset to the sphere, a subset of the sphere into the Euclidean plane. So you think that you want to draw a geographical map of some country. And then you introduce two constants for this map. I want to measure the distortion of the map. I want a measure of the distortion of the map. You see, this double inequality here tells you that the map is a quasi-isometry. This is a standard. Anybody has heard of quasi-isometry? No. Okay, it's fine. So if I have a map from some metric space to another metric space, which is an isometry, what does it mean that it's an isometry? Yes, it means that the distance is preserved. It means that here, the distance between f of x and f of y is equal to the distance between x and y for every x and y. This is an isometry. It's distance preserving. Now, when I say, and this is a standard definition, that the map is a quasi-isometry, it means that the distance is preserved up to a multiplicative constant. That is, if this is equal to 2, if this is equal to 2, means that points which are some distance apart, their image is not 2 times this distance apart. So it's more flexible than an isometry. And from the other side also, if the points, if the images are some distance apart, then it means that it implies that the points themselves are some distance, some bounded distance apart. So this is the definition of this is the usual definition of a quasi-isometry, and I think I wrote it somewhere here. Yes, here. So if you have finite sigma 1 and sigma 2 such that this double inequality is satisfied, it implies that the map is continuous and injective. This is also called by Lipschitz. Yeah, sigma 1 and sigma 2 may vary, yes. If this is valid for some sigma 2, then if I take another sigma 2, which is greater than this one, it will be obviously...
Yes, what happens to the
Okay, you are right. In fact, I come back here. And so here, we take sigma 1 and sigma 2 as the best constant satisfying this. That is, sigma 2 is the smallest constant satisfying this inequality, and sigma 1 is the biggest constant satisfying this inequality. And then the distortion of f, well, I could take sigma 2 over sigma 1, but I want to take log sigma 2 over sigma 1 so that if sigma 2 is equal to sigma 1, which means that the map is an isometry, then I want to say that the distortion is 0 and not 1. Okay? So this is the definition in this paper of the distortion.
Sir,
Yes?
in omega subset of S2,
Yes.
in which metric you are
Always the spherical metric.
and in R2
In R2, I'm taking the Euclidean metric.
so there you are getting same thing for both of them.
Where? I made a mistake. Where?
D of xy.
D same for both you have written, the
Yes, yes, you are right. Yeah, in fact, I did. Yeah, it's a mistake, but it's not really a mistake. But when we put you are right. We put the distance, and then you have to guess whether it is a distance in the range or in the domain. Yes, you are right. I use the same letter here for distances, and you have to understand that this is different. Yeah, thank you very much. Yeah, this is correct. Yes, I make this several times. In fact, it's usual to make this abuse of notation. Yes, yes, you are right. Okay, and then Milnor defines, well, a Milnor minimal distortion map is a map whose distortion is minimal among all maps. I take all maps. So this is, the paper is called A Problem in Geography, and this is a geographical map. I want to build a map where this by Lipschitz distortion is minimal. So he proves then this theorem. So yes.
Yeah. So what does that minimal mean? I mean, it's a subset of R, that set of distortions.
Yes.
Yes. Subset of R. Then I mean, we have a different order, right?
Among all the maps, I want a map of. I'm looking for a map among all possible geographical maps. I'm looking for a method of drawing a geographical map which minimizes this distortion.
Yeah, that's right. But I'm asking, why not minimum? I mean, why do you use the word minimal? Is there any particular reason for that? I mean,
well,
you can say about the
yes.
minimum, right? It's in R. I mean, they're all real numbers.
Yes. Yes. I mean, it's not. Is it obvious for you that a map of minimal distortion exists? Because I mean, if you take the map which contracts everything, or no. I mean, you want a map which is injective, at least, you know. And I don't think that there's no theorem which tells you that a minimal distortion map exists.
Okay.
And this is, I think, here it's. This is the theorem here for existence. I mean, you have to prove this.
Okay.
Yes. So for every set, if the cardinality is at least 3, then there exists a minimal distortion map. This needs a proof. In fact, I mean, if you read the proof, it's really a very complicated elementary topology. He has the map first on a countable set of points, and then he has to show that he can extend and so on. It's really topology. So this is existence. And then he asks the question, so there exists a geographical map, which is minimal distortion in the sense I proved, I explained. Now, the question is about the uniqueness. Is this map unique or not? The differentiability, is this map differentiable or not? The constructibility, is there a way of constructing this map? Because geographer, you want to explain to them how to construct this map. They don't know anything about mathematics. You have to give a method, constructibility. Constructibility of the map and of the minimal distortion. You have so any given omega. How do you find its minimal distortion? This minimal distortion, in fact, is associated to a subset of the sphere omega. Okay, so I'm more or less telling you what he's writing in his paper. He says this problem is unknown. The result is unknown in general, except in one case. The answer to this question is unknown, except in the case here I said is positive. In fact, it's not positive. The answer to all the I copied. I didn't copy correctly. The answer is unknown. The answer is positive. Is unknown except in this case. So the answer is positive in the case where omega is a spherical disk. So what is a spherical disk? It's just I take a point and then I take this is a spherical disk. point, the set of points where the distance to this point is less than a certain constant. This is also a spherical disk. This is also a spherical disk. So this is a spherical disk. In the case where the map concerns a spherical disk, then the answer is positive, and the distortion. So he gives a formula for the minimum distortion in terms of the diameter of the disk, or the radius alpha of the disk, spherical radius. And this is independent of the radius of the sphere. And then he explains what is this map. What is this? He explains what is this, the map which realizes, there's a unique map which realizes this minimal distortion, and he explains, and the map is, it turns out that the map is, we talked about it yesterday. I didn't put the name, but the map is, let me, okay. So I wrote here, F carries each great circle passing to the center of the sphere into a straight line in the plane. So so the map is here. This is the plane. So these great circles here will be sent to straight lines. This point will be sent to a point. These great circles will be sent to straight lines in the plane. The angles are preserved. The angles are preserved. So angle here is equal to the angle here. And what does he say again? The circles here, the circles around this point, the spherical circles are sent to circles. And that's it, I think. That's it. And then he says, I didn't copy everything he says, but he says this map is exactly, it turns out to be exactly the azimuthal projection which I showed you yesterday, which geographers use since 3 or 4 centuries. Without being aware, in fact, that this is the best map. In fact, they had the intuition, but nobody has proved this. And this is not the only instance in the history, you know, of knowledge that the craftsmen, you know, they use something for 300 years, and then a mathematician comes. He says, well, this is the best, the best map, or the best object, or the best thing which could have been used for this. For this situation, so this is the azimuthal. So this is the center. This is the center of the sphere, and the circles are sent to themselves, and so on. The map is not, of course, the map does not preserve angles. So as I explained to you yesterday, these are the ellipses. The ellipses represent the quasi-conformal distortion of the map. They are not all circles, but this map is used often in geography. And then something which I wanted to tell you also at the end of his paper, and also in volume 1 of his collected works, you see the collected works of some famous mathematicians like Raghunathan, or give me a name of a famous Indian mathematician. Yeah, Ramanujan, for instance. You have collected works. They printed after he. For Raghunathan, he's still alive, thank God. But the interest of building a collected works of a person like Milnor, who is still alive, is that after each of his paper he makes some remarks on what is the current situation of the problem. In fact, so he asks these problems 70 years ago, and the problems are still open. Nobody answered them, and he adds to these problems. In fact, okay, so he thinks that there's a similar result for the case where omega is a disk in the spherical or hyperbolic space of any dimension. In fact, even in the hyperbolic space of dimension 2, the smallest hyperbolic space, it is not known whether there is a geographical map which realizes all the problems, all the properties, which has all the properties we stated. But he asks the result for any dimension, and the target space is the Euclidean space of any dimension also. This is now, you see, these questions here are about uniqueness, constructibility, and so on. Now it's a more special problem. Take a geodesically convex region in the two-sphere, meaning a region where, taking a geodesically convex region simplifies the problem. If you want to draw to take the image of a continent like India, it's more difficult. Geodesically convex means that when you take 2 points, then the shortest line between them stays in the set. So this is not geodesically convex. This is not geodesically convex anyway. So this is just a special case where the question is relevant. And I think the same question for convex, geodesically convex regions of the hyperbolic two-plane. If you remember in my first lecture, I told you that there are some natural problems which arise. I gave you this example even from the Euclidean plane. So you take a triangle. I said you take a triangle, and here another triangle. What is the least distortion? Is there a least distortion map taking this triangle to this triangle? And this turns out to be a non-trivial problem. It's a difficult problem. In fact, I wrote at least 3 papers on this, even for Euclidean triangles. The problem of geographical maps is for maps from the sphere to the Euclidean plane. You want to find least distortion maps. Okay, and now there is this question here, which is related also to what we are working on in Teichmüller theory. Suppose you have a distortion minimizing map, then is the distortion constant the same everywhere? Is it necessarily the same everywhere? So yesterday we talked about quasi-conformal maps, and today I will continue a little bit about quasi-conformal maps. And the question is, the question was, so I have, say, a surface, a closed surface, and then another surface here, which has a different shape, and suppose both of them are hyperbolic, or the fact that they are hyperbolic is not very important. Two surfaces equipped with, say, a Riemannian metric, and then you want the surface a priori has no reason to be conformally equivalent. There is no reason that there is a angle-preserving mapping between the two surfaces, right? The question which Teichmüller asked is, what is a best conformal map, a best close to conformal map, or a best quasi-conformal map? This is what he is. This is quasi-conformal means best close to conformal. And in his theory, a best quasi-conformal map, the conformal distortion, you remember this conformal distortion with the ellipses, infinitesimal ellipses, which go to circles, and then the circles which go to ellipses, and then we define the quasi-conformal constant by the ratio of the great axis to the small axis at each point, okay? So in this theory, the quasi-conformal constant it is a result that for a best quasi-conformal map, the quasi-conformal constant is constant at each, on the map, is the same at each map. So here, Milner is asking analogous question. I don't think he had in mind the quasi-conformal theory, but he is asking the same question. For a distortion minimizing map, is the minimum scale constant on the whole surface? Okay, and then number 4, is the maximum scale minimized along the boundary? So this is a question, I mean, it's motivated by potential theory, in fact. In potential theory, I mean, when you study heat propagation and things like that, you end up with something, you want to minimize some energy, and then the heat must be constant on the boundary. So anyway, so this is also a question. So this is a set of questions which is, I think, interesting. Okay, so now I want to, this ends my yesterday lecture. I think it doesn't matter, right? We are trying to understand a few things. Okay, thank you. I just need the light. Yes. Thank you. So let me just remind you of something. So we have, let's say, we have all these geometries. So this is spherical. This is Euclidean. And this is hyperbolic. And we said that being this surface being Euclidean means that when you take a point here, then there is a disk around it, which is isometric to the a disk in the Euclidean plane. There's a more precise definition, which I don't think I know, which I don't think I want to tell you. There's the same definition here. So every point has a disk neighborhood, which is a disk which is isometric to some disk in the Poincaré plane, in the hyperbolic plane. In fact, maybe I should say more. In fact, I want to give a more precise definition. I don't know if you have had such. I know that some of you have, but how many students have had this kind of definition? Yes, I know here. In fact, let me mention something. I want to mention it because also it reminds me of geography. Yes. No, it's not. No, the sphere is not locally Euclidean. You see, if you take a point on the sphere, and if you draw a triangle, spherical triangle, then the sum of the angles we said is greater than two right angles, so it cannot be Euclidean. So we are on the sphere. We are on a huge sphere, which is the you said locally Euclidean? Yes, okay, very locally, infinitesimally. You are right, yes. Yes, you are right. So yes, she's right, in fact. She said, I understand now your question. In fact, locally means for very, very small triangles. The very small triangles look like Euclidean triangles. But here the limit will be 180. The limit of triangles of the angles when you shrink the triangles to a point. Yes, you are right. But when I say, maybe the confusion is due to me. When I say locally, in the sense I explained before, it means that just each point has a neighborhood which could be small or which could be large. In fact, has a neighborhood, has a disk around it, which is the sphere. In fact, this is evident here because we are talking about the sphere, and here a disk which is not necessarily a small disk, right? Even a large disk is Euclidean. Okay, because the metric we are putting on the torus is the metric which arises from this identification of something in the Euclidean plane. So I take a point here. I'm not obliged to take a small disk, an infinitesimal disk. I could take a big disk. It is Euclidean. Even this big disk here is a Euclidean disk, right? Okay, so what I wanted to say, maybe I should give this more precise definition. So, so hyperbolic, let's say in the case of hyperbolic structure on a surface. So, in fact, the terminology here is comes from geography. In fact, those who started this, there's a so the surface. Let's say this is my surface S. There's an atlas on S. What is an atlas? It's a set of maps which cover the whole surface, right? There's an atlas like for an atlas of the world, like an atlas on S. That is an atlas. Well, a collection of di, phi, a collection of di, phi, where di for each I, di is a subset of my surface here. I say I want to take it. I want to take it simply connected. I want to take a disk. And phi I, and this is the domain. This is the geographical map which sends this di into the hyperbolic plane. So this is if I make a picture for each point, I have let's say a small disk here, and a map which takes this this disk into the upper half plane. This is the image. Okay, and I want to say that here on this disk I see like a disk of the hyperbolic plane. So I want to glue them all together. Another point here has this disk neighborhood. Another point here has this. But there must be some compatibility, right? So the compatibility, it's just this thing which the compatibility must say that intersections of the disks, the maps, the corresponding maps in the hyperbolic plane are, well, restrictions of isometries. Let's say isometries, because this disk, which I took on the surface, I can start by sending it to a bigger one or a bigger. But I want some compatibility. I want to measure distances. I want to be able to measure distances here, not only in this small disk, but distances between a point in this disk and in this disk, and a point. I want to measure distance from this point to this point, and there are. I set something on a disk around each point. Okay, so the intersections here, I want them to come from isometries. Of isometries, they should be distance preserving. These maps between different charts must be distance preserving.
So what is the information on phi I? What kind of map phi I?
Homeomorphism. The information on isometries is between the images, the intersections. Yes, it's only there. So I'm gluing some patches, you know, of the hyperbolic plane to make a surface. You can see it in this way. I am gluing these patches to make them this surface, but I must glue by isometries. I must glue them by isometries. Otherwise, I will not get a notion of distance on the resulting thing. These gluings must be distance preserving. Yes. No, everything is right you said, but it's phi I composed with phi j inverse. Yes, this should be isometry. Yes, so she said it better than me. Yes, the phi I are symmetries, but on the intersection, the phi I composed with phi j inverse, whenever it is defined, should be an isometry. I don't think you need it to be smooth. Yeah, in real, yes, but I don't know. I don't think the smoothness is. I mean, the important thing is that it's. I mean, when you say that the smoothness will come from the hyperbolic plane. Yeah, you will carry it on the surface, but I don't think you need to impose it at the beginning. Yes.
Will phi would turn to the isometry?
Huh?
The phi would.
Yes. The phi i's will turn to be isometries after we have put this hyperbolic surface, this hyperbolic metric on the surface. Then the phi i's become isometries. Let me say something. Something else? Yes.
Small question. Sorry, I'm interrupting you. Yeah. So I mean, why H2? I mean, can't you do something about? I mean, discuss H2 by C. I mean,
Yes, yeah, we can. H2, he is right. So if I replace H2 by C, and I do the same thing. So what is the complex? C is a complex one-dimensional manifold. In fact, two real dimensions, but one complex dimension. So a complex surface, or a surface equipped with a complex structure, is exactly what I said. But here, the phi I goes from di into C, and the change of coordinates, whenever they are defined here on these intersections, are holomorphic maps. Biholomorphic, yes. Yeah, holomorphic is biholomorphic, yes. Holomorphic is biholomorphic. Yes, this is a very good remark. So, and in fact, how do I define a surface, a topological surface? Well, topological surface. Yes, the change of coordinates is a homeomorphic. How do I define a projective surface? The atlas goes in the projective plane, and the change of coordinates is a restriction of a projective map. Or then you have many dimensions. This thing you can do in several dimensions, right? The same kind of in dimension 2, things are more things are easy. I mean, more things are easier. In dimension 3, you enter into a world of difficulties, of conjectures, of people who worked during 70 years, 80 years, in fact, different people, one after the other, on the map, on the problem whether there are topological structures which are not on which you cannot put differentiable structures, and so on and so on. So, but on surfaces, it's more or less. I mean, the theory is enough clear so that you can work on problems here. So I wanted to say something. Yes, let me say something because I need this. Okay, let us write here. This is the notion of foliation. This we need, and I think it's in the program of today's lecture, foliation, I think. So okay, so let's start with foliation on the plane. So I have my plane here. I want to draw just a set of lines. So you fill the plane with horizontal lines. This is an example of a foliation. You could make it more, in fact, you could make it like this, so on. This is also a foliation. So what is a foliation? In fact, what is finally what is a foliation? How do I define what is a foliation on a surface? So let me tell you how you define a foliation on a surface. So you remember when we defined a differentiable surface, in fact, I said when we defined a hyperbolic surface, we took an atlas, and then the change of coordinates from here to here has to preserve something. In fact, here it has to preserve the hyperbolic metric. So for a foliation, there is an atlas so this is a collection of I called it I don't like the okay I took the I there's an atlas covering my surface, covering the surface. This is on my surface. This is the I. Taking this into, how did we call this? We didn't give a name for the domain. It's better. Okay, taking this neighborhood of my point to a subset of the Euclidean plane, Euclidean or not, subset of the plane, and then here I have another. This is Dj. This is Phi. Take it here to another subset. And now the important is the change of coordinates. So the change of coordinates, I wanted to preserve. So in the plane, you choose in the plane. This is R2. This is R, and this is R. Then I have naturally a set of lines in the plane, which comes from the fact that I have a product of R and R, right? Horizontal line. So I want this map here. Whenever there's a change of coordinates on each intersection, I wanted to preserve the horizontal lines of the plane. So what do I get on my surface? I get at each point of my surface, I get a well-defined notion of line, because okay, I have a point. I know that I have a neighborhood which sends this to an open set of the plane, and if I take another map, something will be preserved. That is the notion of horizontal line. Means that the horizontal line has a meaning here on my surface. So a surface is equipped with a foliation. A foliation is, in fact, let me use the name, it's something like a geometric structure. Geometric structure means something defined by an atlas with change of coordinates. Okay? So this kind of geometric structure here is called a foliation. So for instance, we talked about the torus yesterday and the day before. So let's take this torus. Let's take this torus. Does it have a foliation? Is there a foliation on this torus? Is there a natural foliation on this torus? Yes. So you see, so if I take these horizontal lines, then for every point, I have an atlas which is like the identity map. You see, which takes me this, which takes this disk around the point. I don't want to say small disk, but it's a disk. And then if another one, if I have another disk here, then well, the set of horizontal lines are compatible with each other. So not only this, but the torus has infinitely many foliations. In fact, I can take any angle here. I can take any angle here. This is a well-defined foliation on the torus, right? So the torus has many foliations. It is an atlas, yes. I mean, the atlas, yeah, but the atlas, the change of coordinates must preserve some set of lines. And here I'm saying that this is a set of lines because this atlas, you know, goes into the Euclidean plane equipped with a foliation, and here is the Euclidean plane. I can see it here directly. Okay. So yes. This is, yeah, this is a good question, but you see these curves here. Yeah, I mean, you don't mean a closed curve when you say a curve. Yes, it is a curve shifting constantly. Yes, it's something. Yeah, it is a curve shifting constantly.
The torus is literally true because the transition.
It is naturally true for the torus. Yes, because I can see it. Now, okay. In fact, before the torus. So let's talk a little bit about foliations. So foliations of the torus. Before foliations of the torus, let's talk about foliations of the plane. The plane itself is a surface. So what kind of foliations I can draw in the plane? So this is a foliation. This is a okay. And so on. This is a foliation. And then I continue, right? Yeah, not everything, but there are a lot of foliations, in fact. On the torus.
So why not everything? I mean, this is a single chart atlas.
The
plane, single chart atlas.
Yeah, the plane. I mean, everything you can draw on this atlas. You're right. You're right. But now let's see. Let's see on the torus. If I start like this, can I continue with a foliation? Okay, let's do it another way. How will I draw this? It has been years I didn't. So you see,
All the straight line will work.
No, not all the straight lines. I want this to be a closed curve of my foliation, and I want this a closed curve, and then I want the lines of my foliation to spiral along this around this one, and here to spiral here also around this one. You see, this one will come here, and then it will continue like this. It will continue like this, and then I want to fill them with huh? No, because I want to fill. Everything is filled, so I want to fill them with. I want to fill the rest with. Yes. So there are foliations like this with spirals. I mean, this question of foliations of surfaces. I will say many things about this. You attain when you go, for instance, to dimension 3, you attain to very difficult problems. You know, I think there was a question for many years whether you see this foliation here. I can also make it differently. So I have my torus, and then I have this will be a closed leaf of my foliation, a circle, and then in the complement of this circle, I want something to spiral along this. Okay. Yes. Yes. It depends on my choice because I decided that the foliation will be defined using these horizontal lines. I don't talk about the vertical lines. Okay, I want to proceed a little bit. Just to say that there are difficult problems, in fact, in dimension 3 on foliations. Foliations in dimension 3. I think that there have been a Fields Medal on some construction of foliations by Novikov, in fact, in 1950s, 1960s. Yes, there are difficult problems. So, but for us, I mean, I want to do things which are simple on the surface. Let me say the simplest things possible. Okay. So no. First about the torus again. So this is again the torus with this identification. So there's something which you must believe. I mean, you must know. I mean, believe me, I tell you, because I'm not going to give you a proof. You can imagine that. So now I take only linear foliations, right? Lines parallel to each other. I'm not doing spirals or things like that, like I did before. Only linear foliations. And the question is, okay, you see, so I follow, when I have a foliation, then these lines are called leaves. I will use this. Yes?
It has to continue like other side.
Yes. So I take a leaf like this. And then it has to continue here. Say. Right? And then I arrive here, and then I have to continue, and then here, and I have. So my question is, does it close? Do I reach a point where? Yes, depends on the slope. Yes, this is an important thing which I will use. So. For instance, if the slope is 0, then I come back to myself. This is a foliation of the torus, but all the leaves are closed leaves, right? If I take so if this is a square, then if I take 45 degrees like this, then it comes back, this foliation of 45 degrees. All the leaves are closed leaves which are parallel to this one. Okay? So the result you need to know here is that if the slope, so any constant slope set of lines will give me a foliation on the torus, right? Because, I mean, you have to, this needs approval, but because when I arrive here, well, I can continue with the same slope. The slopes are compatible with each other. So each point with the definition there, each point will have a neighborhood where there's a well-defined foliation on the plane, and the change of coordinates will preserve this foliation, because I just took it. I just took here the foliation of the plane, which is exactly at the same slope as this one, and this is compatible, right? Yes. So the foliation on the plane is just this one which you extend. Here it's simple in this case. It is this one, the one with the same slope. Okay? So the thing which you need to know is that if the slope is rational, well, all the leaves of the foliation let's say are closed leaves. Closed leaves means compact if and only if the slope is rational. This is a result which I'm not going to prove, and which needs a proof, complicated proof. People who are doing number theory, they know this. They know this very well.
Does foliation have to fill up the space?
I'm taking all these lines, so they fill up. I'm talking here about this foliation, which is the union of all these.
So your space is union of all the lines, all the foliation.
Yes, I have my torus here, and my foliation is filling the space. Yes, I'm taking all these leaves. I'm taking all these leaves parallel to each other, so they have a well-defined slope here. This is the slope. If this angle is rational, then all the leaves are closed leaves. If the angle is irrational, then no leaf is a closed leaf. And furthermore, in the case of irrational angle, every leaf is dense. Every leaf is dense. There are uncountably many leaves. Yes. There are uncountably many leaves. Yes. Yes. In both cases, there are uncountably many leaves. Each leaf is what? A space filling. Yeah, it fills the space. No. This is in the This is in the case of the dense leaf. Yes. If the leaf is closed, then it's not space. In the irrational case, yes. Well, I don't know what he means by space filling, but it fills the space. Yes, it's. So these are the foliations on the torus. No. It's not the only foliations on the torus. It's not. These are the we are talking here only about linear foliations. The foliations with constant slope. This is for foliations with constant slope. Our goal now is to do similar things on surfaces of higher genus, right? This is what I want to do. So what do I want to say more about this, about the torus case? So on the torus, we know that there exists such foliations. Maybe I talk. There's an important notion here which I will explain for surfaces of a higher genus, and this is a question of transverse measure. So this transverse measure is an invariant measure on transversals. So what does this mean? Okay, we don't have a color chalk, but it's fine. So you see, now you understand what is manifold. Did I say a surface is a two-dimensional manifold. Yeah, okay. Let me say something just to finish this for 5 minutes, and then we'll take a break. A surface is a two-dimensional manifold. So this means that, I mean, by definition, a surface, and this means that I have I have an atlas with values in, well, let's say R2. In principle, this is exactly what tells me what is a two-dimensional manifold. But then I can talk here about differentiable two-dimensional manifold, and then I have an atlas with values in R2 with differentiable coordinate chains. So I get a differentiable manifold. I can have here a surface also is, say, a surface is, say, a hyperbolic two-dimensional manifold. I have an atlas with value with hyperbolic. The coordinate change are hyperbolic isometries. So this means that my R2, I have to replace it with by the hyperbolic plane, and so on. So you have different kinds of manifolds. The surface can be a complex manifold in C with holomorphic coordinate change and so on. So each manifold, when you say I have a manifold, you must be more precise. You must say what kind of manifold I have. Complex manifold and so on. So now here I have a foliation. I have a foliation. So this gives me an example of a foliation two-dimensional manifold. This enters in the same big category. So now when I have these foliations, this I'm talking just now about this foliation on the torus. In fact, when I have foliations on some manifold, then I can talk also about hyperbolic foliations. I can talk about complex foliations. I can talk about Euclidean, everything. No, now this concerns the. I wrote it here. The transverse structure of the foliation. The transverse structure of the foliation. Let me say it just in a couple of words. So I have a foliation. Here it's one-dimensional. It could be two-dimensional. It could be n-dimensional. The transverse structure of the foliation means I take a transverse. I take a transverse curve. Or if the foliation is n-dimensional, in an m-dimensional manifold, I take an m minus n transverse. Here it's only one dimension, and I take a transverse curve. So, and I can have various structures on this transverse curve or transverse segment. The thing which is important for us there is that I have a transverse measure. A transverse measure. So when I take this transverse segment, this means a measure in the sense of Lebesgue measure. You know, my transverse arc becomes a space on which I have a measure. On which I have. You don't know about measure. You know measure theory? Yes. Okay. Very good. So I have a measure here. So I can say, well, this set is of measure one, measure two. I can assign numbers. So this is a transverse arc. This is one-dimensional. So I'm talking about measures on the real line or on segments of the real line. So what is proper to this measure? What is proper to this measure, in fact, so that it is a transverse structure? It means that if I move my arc, if I move my arc, this one, I move my arc by letting each point of the arc stay on the same leaf, then the measure is preserved. All these transformations, these are called. Let's complicate. Just if I move the arc so you see, I have when I move the arc, letting each point on the same leaf, it means I have a natural homeomorphism between the first arc and the final arc. Okay? The natural homeomorphism is I take this point, I know that I have moved the arc so that each point stays on the same leaf, so I have a well-defined point on the resulting arc, because there's one leaf carrying this point to this point. So these maps are measure preserving. And this is called a transverse measure for my foliation. And these play a major role in what in this Thurston theory. I will give you more about this after the break. Now it's time for the break? Yeah, okay. In 6 minutes. Yes? Mathematical definition of foliation? I just gave it, in fact. The definition I gave is mathematical, I think. If you want me to write formulas, I'm not able to write formulas. But I tried to explain mathematically what is a foliation, yes. You know, once I was in a geometry seminar. It was long ago, and one of my, in fact, I was a graduate student. I went to a geometry seminar, and then one of my other students told me, where I go. I said, I want to attend this geometry seminar, and he came with me. And after we went out, he told me, you know, now I understand why there are theorems on geometry where one never knows whether they are true or not. This is sufficient. This is okay. Ah, yes, thank you. Yes. Thank you very much. This is a measured foliation on the torus. A foliation where, so this is my foliation, and I have a transverse. On each transverse segment, I have a measure, a Lebesgue measure. My transverse segment is a measured space. And all these measures on the transverse segments are compatible because when I move the segments along, leaving each point along the same leaf, then this natural map from here to here is measure preserving. Now we want to make the same on any surface. Any surface meaning like this one, and so on. This one. Or on the sphere. Let's start with the sphere. Can I draw a foliation of the sphere? Yes. So your friend is telling me, okay, this is, but is this? And then what do I do here?
But sir, it is not measure preserving, right?
It's not a foliation first. There's no foliation on the sphere because I have here these 2 points. I have here these 2 points which are different from all the others because from all other points I have a leaf of the foliation which passes through that point, and here I have no. So in fact this is a theorem. There is no foliation of the sphere. So those of you who did some geometry, some surface geometry, you know that maybe you know if I put here, there is no vector field on the sphere with no zero. Any vector field on the sphere should have a zero. You know this? Or on the disk, right? I cannot draw a foliation of the disk. If I start continuing here, this boundary component, then there's a point here. The thing about vector fields, I mean, people are more familiar with. Students are more familiar with the vector field. At each point you have a vector and so on. And then the vector field has to have a zero somewhere or a singular point somewhere, okay? Yeah, continuous vector field. Yes, she is right. When I say vector field, I say continuous vector field. Yes, there is no foliation continuous vector field. So if you know about vector fields, then you know about foliations, because a foliation is a vector field where you forget about the length and the orientation. You see, in vector field means at each point you have a vector, and then the vectors, the set of vectors gives you integral lines where the vectors are tangent to these integral lines, and then you forget about the orientation, and you get a foliation. So if I have a foliation of the disk, it has to have singular points. Singular points mean just points where the foliation is not a foliation. There's no foliation at all. Tell me, please, a little bit higher. This is, I was thinking about the closed disk. if you talk about if you talk about an open disk, then you must specify what you want the foliation to do on the boundary and so on. This is a closed disk. This is a closed disk. This is a closed disk. Yes. If I talk about open disk, it's a little bit more. I mean, you have to say more. You have to say more. Yes. You see, because yeah, okay. I mean, if your disk is an open disk, then you can throw out the singularities to the boundary. You don't see the boundary, right? Okay. So I'm talking about compact surfaces here. So okay. So now we want to study this kind of yes. So what do you do on the sphere, for instance? You study foliations of the sphere with singularities. And then what is a singularity? You draw a picture and you say this is the model of my, this is topological model for my singularity of the foliations I want to study on the sphere. And then after you have seen this, you can ask me, okay, in fact, I have here a foliation of the sphere with two singular points, right? This one and this one, right? Can I have a foliation on the sphere with three singular points? Is this possible? Yes, I tell you here, in fact, well, here, but then I introduce other kinds of singularities. This is a singularity now. If I introduce this third singularity of this type, then I must introduce other kinds of singularities, and so on and so on.
For any meromorphic form, we can just create a singularity.
Meromorphic forms have singularities, but I think you have to. They have to have an even number of sectors at each singularity. This one here, which is like this, does not come from a meromorphic form. But you are right. This is this is a good point. People who study meromorphic forms, they naturally study foliations. Yes, foliations. Okay, so the thing which I wanted to say here, the thing you see, there's something which you must learn. In fact, topology. Only surfaces with zero Euler characteristic. Have you heard about Euler characteristic? Okay. Have foliations with no singular point. This is not a difficult thing. This you learn, or also instead of this, I can say admit vector fields In fact, because you can, when you have a foliation or a vector field and so on, you can compute the Euler characteristic by taking sums of something, sums of index of the so this has some index, this singularity, this has another index, and so on. And if you have no foliations, then the Euler characteristic is 0. Okay, this is something which, I mean, if you don't know this, you just believe. You just believe this.
So,
yes.
In this diagram, the straight lines are the...
These are foliations with singularities. And to say what is this object singularities, you just draw a picture. And then these are leaves also. They can be dense or they can be whatever. And they are, because they start at a singular point, they are called singular leaves, but they are called also separatrices because here they are separating several regions. Is there any importance for singular leaves? Yes, the singular leaves play important roles. Yes, I will explain, yes. Okay, so now I want to now in this Thurston theory you have we want to study foliations. I wrote it there, in fact, foliations on this kind of surfaces. On this kind of surfaces. So so we must admit singular points, and we must say what is the local model for each singular point. These are foliations with singularities. Of the following form. So I draw pictures, in fact, either like this, or like this, or 5 separatrices, 1, 2, 3, 4, 5, and so on. So this is three separatrices, this is 4, this is 5, and so on. I admit only this kind of singularities. So, for instance, I will not admit this kind of singularity. This is not allowed. And then, from what I said somewhere, that you can compute Euler characteristic from the number of singularities, I know that there are only a finite number of them. Huh? Okay, because why? We have when you compute Euler characteristic of a foliation or a vector field or of a surface and so on, you add some numbers. And these numbers are all of the same sign. Same sign. No, there's a number associated to this. Say this is say -1. This is -2 because I have 4 parentheses. -3. I'm not saying that these are the exact numbers, but it's almost like this. You know, and when you add all these numbers, you find the Euler characteristic of the surface. So it cannot be infinite.
It kind of is a triangular survey, singular.
Yes, because the relation with the Euler characteristic is that from this kind of singularities, you build a triangulation of your surface and so on. So this is an exercise. I mean, no, it's not an exercise. It's quite a result, but it's given as an exercise in Thurston's book, you know, I told you, I gave you three references. And these three references, if you study them, if the three of them, you become a great mathematician if you understand. So the first reference is this paper I said, minimal stretch mass between surfaces, which is on the internet. The second reference is these notes on hyperbolic, the geometry and topology of three manifolds. And the third reference is a book written by Thurston, which is called The Geometry of Three Manifolds, I think, The Geometry of Three Manifolds. The Geometry of Three Manifolds, I think. Otherwise, it's something like that. The Geometry of Three Manifolds, and it's called Volume 1, and it's the only volume. In fact, Volume 2 was never written. And this thing about Euler characteristic from index of foliation is given as an exercise, a half-page exercise. So if you read this book and if you try to do the exercises, most of the exercises I don't know how to do because I have to spend several days on each exercise, and unfortunately I cannot. But if you are willing, this is an exercise. Yes. Okay. So we have foliations with singularities of the following form. Of the following form, either this or this or this, and so on, 6. Okay, now we want to construct at least one. We want to construct at least one, say, and then you will see how you can construct many. In fact, there is a way of constructing many foliations. Let's say. So okay. So we start with. We already saw that a surface you can take two pair of pants and then glue them together, and then you get a closed surface of any genus. I mean, you take 3, 4, 5, 6. Okay. Now the pair of pants I want to now this is no more geometric, it's only topological. I want to draw foliations and then glue the pair of pants together, and I get foliations on the resulting surface. So let's see. I will make pictures here. So this is like this. This is a foliation on a pair of pants, and then I take another one exactly the same. Why not? Exactly the same. It has the allowed type of singularities here and here, allowed type of singularities. And then I glue boundary on boundary.
So what type of singularity?
This is a singularity. It's of this type. It's of this type. 1, 2, 2 singularities. Okay? Yes? The sphere I have taken before, this one, yes? No. When I draw foliations, I don't talk about metric. But this is, we talk only about the spherical metric. But for the foliation, there's no metric. Yes, exact, yes. Okay, so now you glue this part to this part, and what is the problem? Is there a problem in defining a foliation on the surface of genus 2? I find a foliation on the surface of genus 2 with 4 singularities of this type. The identification, yes.
Yeah.
But what would be the problem with the identification?
Like,
Somebody said something? What does this mean? Compatibility of what? Well, this is the leaves. You see, the leaves are trailing everywhere. The leaves are the leaves are everywhere, and each leaf, each point here will go with a point here, and there's no compatibility to worry about. This is when I draw this, it means I have leaves everywhere. The leaves fill the surface. Right? I join, for instance, I'm not obliged, but I join this to this. Maybe I can join this to this. Why not? I mean, this is all topological. I join this to this, and a leaf which starts here, arrives here, you know, and then it continues. This is glued to this, and then it continues here, and maybe this is glued to this, and so on and so on. It wanders in the surface.
so there might be, I mean, if we join, there might be more singular points.
No? Where? From where would they come? Here, when I glue, I'm joining something like that, coming from here, with something like that, all transverse to the boundary, and there is no singular point at all. The leaf will come here, and then it will continue on the next one.
Suppose one of the singular foliation that.
What do you mean? One of the singular foliation? No, one of the singular leaves. Yes.
Singular leaves, yeah.
Yes.
That would attach to a non-singular leaf, maybe.
Yes. Maybe it goes to a non-singular leaf, and then it wanders in the surface. Then.
It has to come to another singular.
No, I never said this. This is an interesting problem. I mean, you have to study what does it happen when if singular leaves, the singular leaves, do they wander what is the closure of a singular leaf and so on. So this is the dynamics people who study this. Usually on much less complicated surfaces, on the torus, on things like that. You know. Yes. Yes, I will talk about this after. Yes. Thank you. So what I want to say here, you see, I want to highlight an analogy, and this will be important for us. Was it last? Yeah, well, I think it was yesterday. We were talking about hyperbolic structures on pairs of pants, and I explained to you two ways of constructing hyperbolic structures on pairs of pants, either by gluing ideal triangles, or by taking right-angled octagons and no, it was hexagons, and gluing the faces pairwise, and then you have these. So this is my hexagon: 1, 2, 3, 4, 5, 6, and then there's one on the other side, and then gluing. Since they are right angles, you get this. Then I said also that you could change the length of the right-angled hexagon. We already said that the 3 determine all the rest. So if you change the 3 that you glue, then it's completely determined, the hexagon, and so on. Okay. Here I'm saying something almost similar, and this is important because in Thurston's theory, there's also an analogy between foliations and hyperbolic structures. So here I'm drawing my pair of pants differently. I'm drawing it planar, so that I can see the foliation. Now in Thurston's theory, something very important, these foliations that appear, most of them, I mean, except in some special cases which are, I mean, which complicate the theory, but at the beginning, the basis, all the measured foliations, all the foliations that appear are measured, transverse measure. There's a transverse measure. You remember I talked about transverse measure there? It means that when I take a transverse arc, I know what is its measure, right? It means in particular that I have a measure on this interval, on this circle here. I have a Lebesgue measure, an additive function, which satisfies some very natural property. I have a Lebesgue measure, and then you see, when I specify a measure, I specify the length. When I specify the length of this, I specify some number here. I specify some number here, and some number here. Let's say A1, some number here which is A2, some number here which is A3. They must satisfy some triangle inequalities, you know, because this will be the transverse measure of this big one. And then there's a transverse measure of this one, and the transverse measure of this one. So I cannot just say, okay, I take here 1 as a transverse measure, and I take here 1 as a transverse measure of this one, and then I take 100 as a transverse measure of this one, because what? You see, because the measure must be, there's a preservation of a measure. The measure of this arc must be equal to the measure of this arc, right? And the measure of this arc must be equal to the measure of this arc, and the measure of this arc must be equal to the measure of this arc. So there are some equalities, but simple equalities like triangle. I mean, in fact, okay, if I say, okay, I want a measure foliation on this pair of pants, where the transverse measure of this is 5, this is 4, and this is 3, they satisfy triangle inequality, then I can find the correct configuration, you know, of singularities, so that I can build this measure foliation. So this. So the idea I want to convey is that you have hyperbolic structures on pair of pants. You glue them, you obtain hyperbolic structures on the surfaces. You have measured foliations on pair of pants. You glue them, you obtain measured foliations on surfaces. There's a classification of hyperbolic structures on surfaces using a decomposition into pair of pants. There's a classification of measured foliation on surfaces using decomposition of the surface into pairs of pants. And there's this theorem of Thurston, which I will explain. I have put it into the program. So we more or less said, I didn't prove that we have this big space, which is called the Teichmüller space of this surface here. This called, let's call it SG. This is G equals 2, G equals 3, and so on. The G is the number of holes here, Teichmüller space of SG. This is a big space. You remember what we said about the dimension? Yes, this is, and in fact, homeomorphic to a ball of dimension 6G minus 6. And then there's also a space which is space of measured foliations on the surface. I want to say now something which is not completely right, but I don't want to go into complications now. The thing is that there's a boundary here. There's a boundary. Like you have like you have hyperbolic space, we said that there's a boundary circle, right? And hyperbolic space of any dimension, it has a boundary sphere. And here the Teichmüller space has a boundary, which is the space of measured foliations. The two spaces glue very well together. The thing which is not correct is that here I have to take projective measured foliations, but let's not complicate. It's more or less this thing, measured foliations. And this whole, the union of the two is called this is the Thurston compactification. The Thurston compactification of Teichmüller space. When you have something which is like an open ball and you glue to it a sphere of the right dimension, then you get a closed ball, and on its boundary you get this. The boundary is that sphere. So this is what I want to explain to you now next. Thank you.
Now we go for tea, and 4:30 there's another talk.
Is it okay?
You can start now.
Okay. Thank you. Okay, thank you, Professor Riddhi, for this invitation to deliver this talk in this Gyan course. So I will speak on this a brief introduction to Finsler geometry. So it is somehow it is related with your this Gyan course given by Professor Athanas Papadopoulos, and it is in fact some of the results also I will include it here in these slides are of it's done by Professor Athanas with his collaborators. So let me introduce about a little bit about the historical development of this Finsler geometry. So in fact, it was started long back by Riemann in his famous lecture of 1854 entitled "On the Hypotheses Which Lie at the Foundation of Geometry," where he discussed about a metric which is more general than square root of a quadratic differential form. In particular, a metric which is fourth root of a quadratic differential form. The origin of Finsler geometry seems to appear in this habilitation lecture. Formally, it was introduced by Finsler in 1918 in his thesis under supervision of Carathodori, and developed by several geometers like Taylor, Burward, Cartan, Bushman, Sasiguchi, Matsumoto, and towards the end of the previous century by S.S. Chern. And still, it's going on. So as everybody knows, this Riemannian metric on a smooth manifold is a smoothly varying family of inner product on the manifold. So those who do not aware about manifold, you just assume, suppose I'm considering U as an open set, and the whole procedure we can develop on some open set of Rn. Now, if you take any curve on even open set of Rn, maybe the arc length of a curve you can determine by integrating its speed. So it actually requires a norm on each tangent space of the point of the curve. Now, a reasonable tool to compute the arc length of curves is a Riemannian metric on the smooth manifold, which is, everybody knows, that is smoothly varying family of inner product on the manifold. Now, one can ask a question that can we talk about family of norms rather than inner products on the manifold? And the answer is yes. Such a norm is Minkowski norm, which I will introduce soon. And a Finsler structure on a manifold is actually a family of Minkowski norm, one on each tangent space of the manifold. So here is a definition of Minkowski norm on a vector space first. So let V be an n-dimensional real vector space. The continuous function f from V to R is called a Minkowski norm if it satisfies the following conditions. So the first condition is that what is called non-negativity condition. So this norm is, it's usual norm of functional analysis, everybody knows. The only difference from the functional analysis norm here, that in functional analysis you take this norm of k chi is equal to modulus of k norm of chi for any real number k, and here I am taking only this positive homogeneity, that is norm of k times xi is equal to k times norm of xi only for positive numbers. What it means that norm of minus xi may not be equal to norm of xi here. So this norm is not symmetric in some sense, right? And this triangle inequality. So if I am considering such a norm, what is called a Minkowski norm. So in fact, there is also a notion of weak Minkowski. So there, here is, there are vectors, so which are non-zero vectors but having norm 0, right? So such a norm is called weak Minkowski norm. But for the moment here, I am only considering this Minkowski norm, and some stronger notion of norm I will consider. I mean, because we are working in differential geometry, so I wanted to introduce differentiability at various level. So I introduced a stronger version of this Minkowski norm. So a Minkowski norm on V is said to be strongly convex if it is smooth on V minus, I mean, non-zero part of the vector space, and the Hessian of f square at any point, at any non-zero point, is positive definite, right? So this is called a strong convexity condition. In fact, if you consider a function f from V to R, which is smooth in non-zero part of the vector space, satisfying this second condition, and this is strong convexity condition, it actually implies this first condition and third condition. So you can think of a strongly convex Minkowski norm as a function from f from V to R satisfying this positive homogeneity condition and strong convexity condition. So the consequence of this strongly convex Minkowski norm is that for any non-zero vector it must be positive, right? And the second, this triangle inequality comes, I mean, as a consequence of this strong convexity condition. So I mean, in some books, this is strong convex Minkowski norm is said as Minkowski norm itself, and in fact, Finsler structure is I mean, in some sense, a smoothly varying family of this strongly convex Minkowski norm, which I will soon define. Now, here is a notion of indicatrix. It's actually a kind of unit sphere for the given norm. In Finsler geometry, it's well known by indicatrix. So, the unit sphere centered at origin is called indicatrix. It's very important for our purpose. And the geometrically, this is strong convexity means that this indicatrix is actually a hypersurface of strictly positive Gaussian curvature, right? So this strong convexity, this implies that as a hypersurface, this is indicatrix as strictly positive Gaussian curvature. Now, so for this strongly convex Minkowski norm, among LP spaces, only this is strongly convex Minkowski norm if and only if this P is equal to 2. That is only Euclidean norm among all the LP spaces or strongly convex Minkowski norm. Although you see this, if you just consider only Minkowski norm in this previous definition without this strong convexity condition, for all P it's actually Minkowski norm. But for strong convexity, only this Euclidean norm satisfy this condition. In fact, for P lies between 1 to 2, this smoothness condition is violating, while when you take any P greater than 2, this strong convexity condition is violated. Now, the next definition, next example of a Minkowski norm, if you take a Euclidean norm on R2, right, this y1 square plus y2 square, if you take any vector y in R2 with coordinates y1 and y2, and you take any real number b, positive real number b, which is less than 1, then if you define a function f from R2 to R like this, it's actually satisfy all the condition of a strongly convex Minkowski norm, and therefore it is strongly convex Minkowski norm, right? You can prove that it's the square, the Hessian of the square of this norm is actually positive definite. Now, how it differs with this Euclidean metric, there are some, these are propositions, these are very important propositions. So, in most of our discussion, I will only talk about the results. Rarely I will prove anything, but just because I'm giving some overview about this Finsler geometry, so I will say mostly about the results rather than going in the proof. So, how this Minkowski geometry is differ with this Euclidean geometry? So let Rnf be a Minkowski space. So here I am considering just Minkowski metric, not strongly convex Minkowski metric, and delta be this Minkowski metric induced from f, that is delta, and the distance between 2 point x and y is defined by this fx minus y on Rn. then this delta is Euclidean if and only if the ball centered at any point A and any radius r is an ellipsoid. So in fact, it's a necessary and sufficient condition for this distance induced by this Minkowski metric is Euclidean, is that this ball centered at any point, in fact you can take your point as origin, and any radius is an ellipsoid. And here is second important proposition. So if delta B is a Minkowski metric on Rn, then every isometry of delta is an affine transformation of Rn. And the group of isometries of delta is actually conjugate to subgroup of the group of isometries of Euclidean space, right? Further, this isometry is conjugate to the full group En. So here it's conjugate to subgroup of group of isometries of Euclidean space, and your delta becomes Euclidean if and only if it is conjugate to the full group of Euclidean isometry. This is the distinction between how you can differentiate this Minkowski metric with Euclidean metric. Now, this result is for strongly convex Minkowski space. This result is very much useful for further investigation. So, if Rn with F be a strongly convex Minkowski space, then this square of the norm is always C infinity away from the origin. But at the origin, it is just C1 and it has all derivatives as 0. But the third condition is very important, that it is C2 at origin if and only if F is Euclidean. So this is again, a kind of differentiation between this Minkowski space and Euclidean space. So if this square of the norm is C2 at origin, then this F is Euclidean, and other way it's trivial. Now, a Finsler metric on a smooth manifold is a continuous function f from tangent bundle to R such that its restriction to each tangent space is actually strongly convex Minkowski norm. So for me, a Finsler metric on a smooth manifold is actually a function from tangent bundle to R such that at non-zero part of the tangent bundle it is smooth, and its restriction to each tangent space is actually strongly convex Minkowski norm. This function f is called Lagrangian of the Finsler structure. And this Finsler structure is called, so in general it is not reversible. So the length of this vector minus chi, it should be at one place it is plus chi. So the length of this minus chi in general is not equal to the length of the vector chi. And if f of minus chi is equal to f of chi for every chi and at every point, this Finsler structure is said to be reversible. Now, here are some examples. So, suppose F0 be a Minkowski norm on Rn, and you just, define at every point, you just translate this Minkowski norm, you just define by this translation. So, this function f from the tangent bundle of Rn to R is defined like this F0 of chi. You don't care about the point x. So, everywhere you have just like Euclidean metric. So, you have the same Minkowski norm at every tangent space. So, such structures, in fact, considered to be the flat space in Minkowski geometry. Now, a Riemannian metric on a manifold again defined a Finsler structure. So, you have this G as a Riemannian metric. So, f of x chi is actually equal to square root of this gx of chi chi. So, this actually defined a norm of the vector chi, and this I'm talking about the Finsler structure induced from the Riemannian metric G. Here is another example of a Finsler metric, what is called the famous example, Rander's metric. So, if G be a Riemannian metric on the manifold M, and theta is a one form, and the condition is required that this one form, the length of this one form with respect to this Riemannian matrix should be less than 1. I mean, a simplest example just I said in for the Minkowski metric actually, right? We have just considered this Euclidean metric. A slight deformation of the Euclidean metric was the Render's metric, and that was an example of the Minkowski metric. So here on a manifold, if you have a Riemannian metric and a one form, you can define a Finsler metric in this way, that the Riemannian norm and deform by this value of this one form on the vector chi. So this is, I mean, it can be proved that it's actually it satisfies all the condition of a Finsler metric, and this is called Render's metric. You see here, indicatrix is, I mean, the unit sphere in the Euclidean plane is well known. I mean, you translate, and in every tangent space you get Euclidean unit spheres. These are the indicatrices in Riemannian plane, right? So these are, I mean, symmetric ball, and at every point in every tangent space you have these symmetric ball, and these are the indicatrices in the Finsler plane. So at every point these are indicatrices. These are just strongly convex ball. Strongly convex. I mean, the interior is ball and the boundary is indicatrices. Now, the advantage to define this Finsler metric is that we actually wanted, as I said in the first slide, we actually wanted to compute the length of this curve, and now you can define the length of a curve. So the length of a curve gamma defined on some interval I is given by this formula. So you just, I mean, measure the speed of the, which is the, I mean, norm of the velocity vector, and you just integrate to get the length of this curve. And when you can measure this piecewise smooth curves, their length, you can define the distance function. So the distance is the infimum of length of piecewise smooth curves joining the 2 points. Now, interestingly, because of this non-reversibility condition, because this norm of minus ji was not equal to norm of ji, and therefore the distance here is not symmetric, right? And in fact, the length of any curve is not equal to length of its reversed curve, right? So if gamma is a reverse curve, its length may not be equal to the length of gamma, right? And therefore, its distance satisfy all the condition except this symmetric condition, right? So as we saw that a Riemannian metric is actually an example of a Finsler metric. Any Riemannian metric induces a Finsler structure. So the Hessian of the square of this f square, I mean, why we consider this a strongly convex Finsler metric, although you already have a Minkowski structure. So the reason is that we actually wanted, in some sense, an inner product induced from this Minkowski metric, and this Hessian of f square actually give, in some sense, a kind of inner product on the manifold. So the Hessian of f square induces a direction dependent inner product. So here you see, in Riemannian case, in every tangent space you have a unique inner product, but here in one tangent space this inner product is direction dependent. It's direction dependent, although you see, because of this homogeneity condition of this norm, it's direction dependent. I mean, this inner product I, the inner product of v and w is given by this formula. If v and w are two vectors with components, say this vi, wi with respect to some coordinate system, then their inner product is given by this formula. And the Finsler metric and this G, this inner product actually is well known by fundamental tensor. So the Finsler metric F and the fundamental tensor G are related by this formula. Here is a very interesting quantity what was introduced by Cartan. So it's well known by Cartan tensor. So it's actually the third derivative. I mean, third derivative of this square of this square of this Minkowski norm. So suppose its component are this, say, given by C, I, J, K. They are actually when you write in terms of the fundamental tensor, it's actually the vertical derivative of this metric tensor, and you can see that it is equal to 0 if this Gij is independent of this direction. And when this metric tensor is independent of the direction, your metric is actually Riemannian. So this Cartan tensor is important in the sense that if it vanishes everywhere, if it vanishes in every direction, then your Finsler metric is actually Riemannian. So the vanishing of Cartan tensor implies your Finsler metric is Riemannian. Yeah. Now let us come to the next stage, that you can measure now the length of curves, and now here is the energy functional. So for any curve gamma, you can define its energy functional as the integral of square of this norm. And the geodesics are actually the critical curves of this energy functional. You can also prove that the critical curves of length functional with constant speed curve is equivalent to the criticalness of this energy functional. So I mean, if a curve gamma is a critical curve for this energy functional, is same as it is a critical curve for the length functional, and it should have constant speed. So the geodesics are defined as the critical curve for energy functional. So it means that it's also critical curve for length functional, that is, you can talk about the minimizing length, and it should have constant speed. Now in local computation, the geodesics are given by a system of second order differential equation, exactly same as you know in Riemannian geometry. The only thing is that here this gamma ijk, what are called Christoffel symbols, they are only function on the manifold, but here these quantities are functions on the tangent bundle, and therefore you have a highly nonlinear second order differential equations. But still, because of sufficient smoothness, you can talk about their solution. So if you have a point, initial point and initial direction, at least for start time, you can have a solution of this differential equation. And therefore you can talk about the exponential map. So for a vector u, given initial vector u in a tangent space, let this gamma ut be a geodesic with initial value, initial point and initial velocity, then this exponential map is defined by exactly, it has same definition as you know in Riemannian setup. And you know in Riemannian setup this exponential map is C infinity, but in this Finsler setup, because of you know this the result we proved for this Minkowski norm, somehow it is used here to prove this exponential map is only C1 at origin, and it is C infinity away from the origin. So exponential map in Finsler geometry is only C1 at origin, whereas it is C infinity away from the origin. And interestingly, it is C2 at origin. It's a result by Akbarzadeh that if it is C2 at origin, if and only if it is C infinity at origin. And in that particular case, this Finsler metric is a special name, what is called a Burward metric. So I'm not going in detail about this Burward metric, but I just wanted to emphasize that if it is if you just increase the smoothness of this exponential map by from C1 to C2, it must be C infinity. Now here is, I mean, this oscillating Riemannian metric. So it's a Riemannian metric associated with a Finsler metric, and it's very much important for computation of curvature actually, right? So suppose MF be a smooth manifold with a strongly convex Finsler metric, and x0 xi0 be a point in this non-zero part of the tangent bundle, that is, this vector is non-zero. Now a vector field V defined in some neighborhood of the point x0. So this vector field is said to be geodesic extension of xi0 if the integral curves are geodesics of the Finsler metric F, right? In particular, this V, it should not be zero in the whole neighborhood, right? So you are considering a geodesic extension of a vector, but it should not be zero in the whole neighborhood. If such an extension if you have, then I am defining this oscillating Riemannian metric of a Finsler metric F in the direction of this vector field V, and it is defined like this. So what it means, that at every point you are fixing a direction. So if you are fixing a direction, you have one inner product. That this inner product coming from the Finsler metric is direction dependent. So if at any point you fix the direction, you get exactly unique inner product in that tangent space. So if you have a vector field in some neighborhood, so you just consider that vector field as representative there, and therefore in that tangent space you have exactly one inner product, right? And that is called oscillating Riemann. So in that sense, in that way, in the whole open set, you constructed, a family of inner product, and that is just parameterized by the point, and therefore is a Riemannian metric. And now you have a Riemannian metric, so therefore now you can talk about all the geometry what you know about Riemannian geometry. In particular, you can talk about the Riemann curvature tensor, right? So Riemann curvature here, everybody knows. So in you have a kind of Christoffel symbol, as we defined while I was defining this geodesics. So you know this Gi is a quantity. These are called spray coefficient for in Finsler geometry. And in terms of the spray coefficient, you have this formula for Riemann curvature, and that are exactly the Riemann curvature of the this Riemannian metric defined in the previous slide. So in some sense, we have a notion of Riemann curvature in Finsler geometry, and this Riemann curvature, the notion of Riemann curvature induces the notion of flag curvature, which is analog of the sectional curvature in Riemannian geometry. The only thing is that here, in sectional curvature, in every tangent space you fix a two-dimensional subspace, and corresponding to that two-dimensional subspace you have a notion of sectional curvature. But here, in that two-dimensional subspace, again I am fixing a pole, right? I am fixing a pole xi. So with respect to that flag pole, I am defining this flag curvature as it has the same formula. The only thing is that everywhere, almost all the things are direction dependent. So that direction, if you fix a direction, it is called the flag curvature at a point x in direction of xi. So if you fix a flag pole xi, and in a two-dimensional subspace P in tangent space Txm, and suppose I'm taking this V as a vector transverse edge, that is this xi and V, they span this subspace P, then the flag curvature is given by this formula. It's exactly has the same formula as you know in Riemannian geometry. So here it depends on the point, it depends on the flagpole, it depends on the two-dimensional subspace P. But it will not depend on this transverse. You can take any transverse edge, and it can be proved that it is independent of this transverse edge V. So it depends on the point, it depends on the flagpole, and it depends on the cloth part of the flag, that is the two-dimensional subspace. And that is why it is called flag curvature. Okay, so that I already said. So in Finsler geometry, a Finsler metric is said to be constant flag curvature if it is independent of this chi, independent of x, and independent of p, right? So for every x, for every chi, and for every p, if this flag curvature is constant, we say that it is of constant flag curvature. It's said to be scalar flag curvature if it is independent of this two-dimensional subspace that only depend on x and this flag pole. So if cloth part disappear in the formula, we say that it is of scalar flag curvature. And as everybody knows that in a Riemannian metric of constant sectional curvature is completely classified. The classification is known that locally it's Euclidean or spherical or hyperbolic metric, but in Finsler geometry it's an open problem. This Randers metric, what I defined in the previous slides, only this case of Randers metric of constant flag curvature was completely classified, and I mean, but for different metrics people classified and is going on, but in general it is not done yet. Okay, now let us come to another interesting example, what is called Funk metric in a convex domain in Rn. So let us consider a convex set omega in Rn and what is called this tautological Funk-Finsler structure, right? So this omega is a convex set. So at each point of omega, you can think of this omega itself as a unit ball in the tangent space of that particular point, right? So for example, if this is my convex set and you take so this is suppose this is a convex set, for the moment you can assume as a unit ball, right? And it may not be this as it's look like, so maybe I can draw some picture here. So maybe you can think of, suppose this is my convex set and take a point here, and I'm declaring that this is unit ball, this is my unit ball in the tangent space of the point this, right? You take another point, right? This point, for this point you identify your tangent space with your space Rn, and in that tangent space you can think of the same set as unit ball centered at this particular point. So for various point, this ball is fixed, and you can think of that ball as unit ball in that particular tangent space of that particular point, right? So in this way you can have a notion of norm in every tangent space, right? If you know this unit ball in a tangent space, you can talk about the norm. For example, so if this is, suppose this is my unit vector and you want to measure the length of this vector, right? So if suppose this is 2 times, you can say yes, this is the, I mean, the length of this vector is 2. So the length of any vector, if you want to measure the length of a vector this, you just see that how much it may be k times. If this unit vector is this vector, then its length is k. You can use this the positive homogeneity, right? But the length of this vector is 1 here, it may not be equal to the length of this vector. The length of this vector is, say, here 1, the length of this vector is also 1. So it may not be symmetric, right? So if you know the unit ball in every tangent space, you can have a Finsler structure on that particular manifold. So here this special Finsler structure is called tautological Funk-Finsler structure, right? So suppose at a point x you want to measure the norm of this vector chi, what you have to do, you just see that x plus, suppose 1 upon t times chi. I mean, suppose it's 2 times chi is intersecting this boundary, that is 2 times xi is this unit vector, it means this norm of xi should be 1 upon 2, right? So that is given here. So infimum of this t, when it's going to intersect this point A, and you have to take the infimum of that real number t. So for instance, if 2 times xi is at the boundary, it meets at the boundary, then the norm of xi is equal to 1 upon 2. So I mean something like that. So you can have this Finsler structure, and this is called Funk-Finsler structure for this convex set omega. In particular, if this convex set omega is Euclidean unit ball, if this omega is Euclidean unit ball, you know, this x plus xi over this fx xi, which was the norm of this xi, it will be a point on the boundary. So its the square norm is equal to 1, and a simple computation gives this quadratic equation. And if you just solve, I mean, you can see this is the angular bracket as the inner product, Euclidean inner product, and this is the Euclidean norm of xi, Euclidean norm of x. So a simple computation gives this formula. So the Finsler structure for this, I mean, this unit ball is, I mean, Funk-Finsler structure for this unit ball is given by this formula, right? You can see here this first expression. Those who know the various models of hyperbolic geometry, they must know that this is actually the Klein metric in open unit disk. This is Klein metric, standard Klein metric in open unit disk, and this is a one form in open unit disk, right? So this Finsler structure is actually the sum of a kind of Riemannian metric and a one form and a one form, and in fact this one form is a very special one form, is closed one form, and this is the standard Klein metric, right? And by some simple computation, you can observe that this Funk-Finsler structure is actually a Reinders metric given by this previous equation. It is called Reinders metric because the sum of a Riemannian metric is a kind of deformation of a Riemannian metric by some one form. And the geodesics of this Funk-Finsler structure on the unit disk, they are line segments. So this is an interesting remark that in this case, the geodesics are the shortest paths are actually the line segment in open unit disk. And further, the distance induced by this Finsler structure is actually given by this formula. So here, so suppose this is my unit disk and you have 2 points x1 and x2, and you take this ray, suppose this is my x1, this is my x2, and it intersects this boundary at a point A. So now you compute the distance from x, this is the Euclidean distance from x1 to A, Euclidean distance from x2 to A, and take its log. So for instance, you can see that, I mean, when this x2 going closer and closer to this boundary point, this distance, I mean, becomes closer to 0, and this becomes infinity. So as this x2 going closer and closer to A, the distance from x1 to x2 going to infinity. So I mean, it's a kind of you see here it's a forward complete. It's a forward complete Finsler metric, but the distance from x1 to x2 is not equal to distance from x2 to x1, because when you compute the distance from x2 to x1, you have to take this ray from x2 to x1, and it will intersect somewhere at the point B, and then you have to take the ratio of this x2 to B and x1 to B, right? So in that sense, it's obvious that the distance from x1 to x2 is not equal to distance from x2 to x1. And further, as I already talked about the flag curvature, it can be shown that this Funk-Finsler structure has constant flag curvature minus 1 upon 4. It has constant flag curvature minus 1 upon 4. And it's a forward complete, but not backward complete. It's not backward complete. The next example of Finsler metric is the Hilbert metric. Now, the Hilbert-Finsler structure in a convex domain omega is actually the arithmetic symmetrization of the tautological Funk-Finsler structure. So, if fx xi be the Funk-Finsler structure for a domain omega, then you consider this reverse Funk structure and you take its arithmetic symmetrization, right? So, this Hilbert-Finsler structure is the arithmetic symmetrization of Funk-Finsler structure. And here you can see the symmetry comes, right? So, if you take x1, x2, and suppose this ray from x1 to x2 hits this boundary at the point A, and this ray from x2 to x1, it hits this boundary at the point B, this both point A and B will appear in the formula of the distance. So, here is the proposition with respect to this Hilbert-Finsler structure. So, the Hilbert-Finsler structure is exactly given by the formula of the Klein metric. So, for unit ball, if your omega is the unit ball, if your convex domain is unit ball, for unit ball, the Hilbert-Finsler structure has exactly the same formula as your Klein metric of hyperbolic geometry. Here again, the geodesics of this Hilbert structure on open unit disk are line segments in open unit disk. The distance formula is just, the arithmetic symmetrization of what we got in the Funk formula, that is x1 minus a upon x2 minus a and plus log of x2 minus b upon x1 minus b. You can also see that this x1, x2, a and b, this is actually cross ratio of these 4 points lie on a line, right? So, this Hilbert distance has this interesting formula. And this Hilbert-Finsler structure on open unit disk is also of constant flag curvature, but it's of constant flag curvature -1 because it's a form of Klein metric, and Klein metric has a constant flag curvature -1. And this Hilbert metric is both forward as well as backward complete. Okay, now here is the interesting characterization for this Hilbert metric. So, the Hilbert metric F in a bounded domain omega with a smooth, strongly convex boundary, it is Riemannian if and only if this omega is an ellipsoid. So, if it is an ellipsoid, so for instance, we just computed for this omega in the unit Euclidean ball, right? And you saw that it's a Klein metric, which is a Riemannian metric. So, for ellipsoid, this Finsler metric is Riemannian. It's actually if and only if condition. So, if it's not ellipsoid, it cannot be Riemannian. And this is an interesting characterization. If F is a strongly convex Finsler metric on a bounded convex domain omega, then F is Hilbert metric of that domain. This Finsler structure is actually Hilbert metric if and only if this projectively flat means this the geodesics are line segment. So, this projectively flat has a meaning that the geodesics are line segment. So, if and only if the geodesics are line segment, it's complete and has constant -1 constant negative flag curvature, right? So, this is an interesting characterization of this Funk-Pervert metric. So, I will give the proper reference for this. In fact, it's appeared in a book by Professor Papadopoulos and Triano. So, I will show in the references. So, all these theorems are proved there. Those who are interested can go through it. Now, further, you can see this Funk metric in various perspective also, right? So for instance, everybody know, like in hyperbolic geometry, so this Lorentzian metric is a non-positive definite metric in R3. In fact, you can think of in Rn plus 1 also. So it's Lorentzian metric. It has signature, I mean, minus 1, 1, 1, 1 n times. So it's a non-positive definite Riemannian metric. But when you pull back this Lorentzian metric on hyperboloid of upper sheet of hyperboloid of 2 sheet is actually a positive definite Riemannian metric, and what is called hyperbolic metric on the unit disk. And it depends on what immersion you are considering. You can get Klein metric or Poincare metric on the open unit disk. So in a similar way, you can also construct a non-positive definite Randers metric on upper half space whose pullback on hyperboloid of 2 sheet is exactly the Funk metric in unit disk. And that is, it was, recently pointed out, and the paper, appeared last year. So this was the Lorentzian metric in R3, and it was defined by this one form. So to get a non-positive definite Randers metric, and its pullback on the upper half of the hyperboloid of 2 sheet is actually the Funk metric. And this is another interesting realization for this Funk metric as a solution of Zermelo navigation problem. So Zermelo actually posed and answered the following question, that if you consider in calm water, right? So suppose some ship is sailing in this calm water from one point, from this point, and if there is no flow in the water, in unit time it reaches same distance, same Euclidean distance, right? But suppose there is a flow of water, and in unit time this you have to sail the ship. It will take some, the path like this. In unit time, in direction of the water it may go some longer distance, and against the water, smaller distance, something like this, right? So this is my unit ball for this for this boat, right? Now, in fact, you can prove that the shortest path here with this flow, it's not actually the geodesic of a Riemannian metric. It turns out that it's a geodesic of a Finsler metric, in fact Randers metric. So if this convex set, so you can take any, in fact, convex set omega which contains the origin, then the Funk-Finsler structure gives the solution of Zermelo navigation problem for this special flow of the vector field given by this Zx is equal to x, right? For this special vector field, its solution of the Zermelo navigation problem. So this Funk metric is also interesting from this viewpoint. Now you see this this Funk metric, which was we defined that the distance between 2 points in a convex set was this log of x1 minus, so it was defined like this. So for any convex set, this x1, x2, suppose this ray intersect this boundary at a point A, x1 and x2. So it was defined like this: the x1 minus a, the Euclidean distance from x1 to a, and Euclidean distance from x2 to a. You take the ratio, take the log, that is the Funk distance between 2 points. Now this x2, the perpendicular distance from x2 to this hyperplane, and the perpendicular distance from x1 to hyperplane, right? And by similarity you can prove that the supremum of this exists when this is strictly convex. It exists at when this hyperplane is tangent at the point A, and there the ratio of x2 to a and x1 to a is same as the ratio of these these two distances. I mean the distance from x2 and x1 to this hyperplane, right? So, but through this approach, I mean several difficult problem, I mean, can be solved very easily. For instance, if you want to prove the triangle inequality through this approach, it can be proved very easily. So somehow this ratio of distances, they are important, and it was considered to define this variational Funke distance. Now they actually they also generalize it to the spaces of constant curvature. So here, in Euclidean geometry, this you consider the two triangles, the two similar triangles, say this A, B, C and A, B dash, C dash. And here this sign of A you can write as ratio of BC is to AC, or B dash C dash to A dash C dash. But in spherical geometry, when you consider the ratio of length of these sides, you have to consider here the weight function, right? So it's not BC upon AC. In fact, it's sine of BC is to sine of AC. In spherical geometry, only simply the ratio of the length of the sides will not appear, but it will be this weighted by this sine function. That is, sine of A is actually equal to sine BC upon sine AC, or sine B dash C dash sine A dash C AC dash. And similarly, in hyperbolic geometry, this will appear as weighted by this hyperbolic functions. And then they define this distance between 2 point x1, x2, what is called the Funke metric in the negative curvature spaces, as the log of sine hyperbolic. Distance from x1 to A, hyperbolic distance from x2 to A, take their sine hyperbolic, take the logarithm, and that is the distance between 2 points in the negative curvature in a convex set in negative curvature spaces. And they also computed this Finsler structure there. In a similar way, they computed for this positively curved spaces. So suppose x1 and x2 be 2 points in a convex set omega on this sphere. Suppose this omega is a convex set on the sphere, and suppose this geodesic, this great circle x1 passing through x1 and x2 intersect the boundary at A. So you compute the spherical distance from x1 to A, x2 to A, take their sign and take the ratio, and that is the Funke formula for a convex set on the sphere. And again, they computed the Finsler structure for this Funke metric given by this, and the local, in fact, infinitesimal structure of this Funke formula in local coordinate system. It was recently we have computed, in fact, and in fact we got a formula for all the three spaces, for Euclidean space, for hyperbolic space, for spherical space, in a single formula. Is given by this. So I think my time is over also, and it's the best time to stop. So those who are interested to go through, it was just an overview of the Finsler geometry, some aspect of Finsler geometry, you can say, and most of the results are already proved in. I mean, those who are interested can go through this interesting book of Papadopoulos and Traiano, and this paper also, weak Finsler structure and Funke weak metric. So thank you very much for your patience, and I'm happy if you have any query or question.
Hello, can you hear?
Yes, yes, yes.
Yeah, so are there any questions? No, thank you very much.
Okay, okay. Thank you, thank you.
It would have been nice if you could have
Yeah, yeah, definitely.
been able to come. So.
Yeah, yeah. So in fact, the train through which I was about to come, it is still not reached the New Delhi railway station. It's too
Yeah, I
late.
know.
Too late. Too late. Yeah, yeah.
We'll probably reach the Mahakumbh.
Yeah, yeah, yeah. Yeah, yeah. Okay. So thank you, thank you, thank you.
Okay.
Okay, okay.
Thank you. Bye.